A solar farm can be fully financed. A data center can be ready to break ground. A factory can have political support, tax credits, and customers waiting. But if one piece of heavy grid equipment is missing, the entire project can still sit idle. That piece is not a battery. It is not a solar panel. It is not a turbine. It is not an AI chip. It is a transformer. The massive electrical machine that allows power to move from one voltage level to another. Across the United States, transformers have become one of the quietest but most serious bottlenecks in the energy build-out. This shortage does not always look like a crisis. It looks like waiting for a production slot, waiting for a delivery date, waiting for a substation upgrade, waiting for the one machine that determines whether a project can actually connect to the grid. And that is the strange reality of America's energy transition. The country can announce more solar farms, more batteries, more factories, more data centers, and more transmission projects. But if the grid hardware does not arrive on time, the future does not arrive on time either. So the real question is not just how much power America can build. The real question is, what happens when the projects America cannot afford to delay are slowed by equipment it cannot get fast enough? The United States is trying to electrify more of its economy, modernize an aging grid, build renewable energy, power artificial intelligence infrastructure, expand domestic manufacturing, and improve energy security, all at the same time. But the physical equipment behind the grid does not move at the speed of policy announcements or investor presentations. And that is the deeper story. The transformer shortage is not just a supply chain inconvenience. It is a warning about the next phase of the energy transition. Because the future of energy will not be decided only by who can build the cheapest solar panel, the biggest battery, or the most powerful data center. It will also be decided by who can manufacture, deliver, install, and maintain the heavy industrial hardware that makes the grid work. For American viewers, this matters because this is not only a clean energy issue. If the United States wants more solar power, wind power, battery storage, transmission capacity, factories, AI data centers, electric vehicles, heat pumps, and broader electrification, it needs transformers. That is why this shortage is so important. The grid is being asked to replace old infrastructure, connect new generation, serve new loads, and become more resilient against storms, heat waves, cyber threats, and physical attacks, while electricity demand begins rising again after years of relatively flat growth. For a long time, many Americans thought of the grid as something stable in the background. Power was just there. The wires worked, the substations operated, the equipment quietly did its job. But now the grid is no longer just background infrastructure. It has become a strategic platform. It determines where factories can be built, where data centers can expand, how fast renewable energy can connect, and whether industrial policy moves from speeches into steel, concrete, copper, and megawatts. And transformers sit right at the center of that system. A shortage of transformers does not make headlines like an oil price spike or a blackout, but it can quietly delay the projects that are supposed to prevent future energy problems. When enough projects are waiting at the same time, the delay becomes systemic. To understand why this matters, it helps to understand what transformers actually do. Electricity does not move through the power system at one fixed voltage. It is generated at one voltage, transmitted at another, stepped down through substations, and finally delivered at safe, usable levels. Transformers are the machines that make this possible. A generator step-up transformer raises voltage from a power plant, wind farm, or solar project so power can travel efficiently over long distances. Closer to where electricity is used, substation and distribution transformers step voltage back down for cities, factories, businesses, and homes. In simple terms, if transmission lines are the highways of the grid, transformers are the interchanges. Without them, electricity cannot move properly between different parts of the system. A solar farm without a transformer is not really connected power. A data center without the right grid equipment is not truly ready to operate. A factory without adequate electrical infrastructure is just a building waiting for power. The transformer is the conversion point between intention and operation. And unlike many products in the modern economy, transformers cannot always be mass-produced quickly in a simple, standardized way. Large transformers are heavy, complex, and often custom-engineered. They require specialized steel, copper, aluminum, insulation systems, cooling systems, bushings, engineering design, testing, and skilled labor. They are not easy to stockpile because specifications vary across projects and utilities. They are not easy to move because large units can weigh hundreds of tons and may require special rail, heavy haul trucks, permits, and specialized handling. And they are not easy to replace quickly if something goes wrong. The equipment is too large, too expensive, too specialized, and too slow to produce. That is the industrial reality behind the shortage. The conflict now is not simply demand versus supply. It is speed versus physics. Developers, utilities, data center companies, manufacturers, and policymakers all want to move fast. But transformer production moves at the pace of heavy industry. A software company can scale a digital product almost instantly compared with the power sector. A data center company can announce a multi-billion-dollar campus before the public fully understands its power needs. But a large transformer still has to be designed, manufactured, tested, transported, installed, and integrated into the grid. That process cannot be compressed indefinitely. This is where the energy transition becomes more complicated than the public narrative often suggests. The public conversation often focuses on generation. How many gigawatts of solar? How many wind turbines? How many batteries? How much clean energy capacity? But generation is only one part of the system. The grid has to accept the power, substations have to handle it, transformers have to convert it, transmission has to move it, and distribution has to deliver it. If any one of those layers becomes constrained, the whole build-out slows down. This is especially important for renewable energy. Solar and wind projects can often be built faster than major grid infrastructure. A solar farm can come together in months once financing, land, permits, and equipment are in place. But the substation and interconnection equipment can take much longer. That creates a frustrating paradox. The generation technology may be ready, but the grid connection may not be. The bottleneck is not always the megawatt. Sometimes it is the missing machine that allows the megawatt to enter the grid. This is also why the transformer shortage hits more than renewable energy. AI data centers are now competing for power on a massive scale. These facilities need reliable, high-capacity electrical service. They need substations, grid upgrades, backup systems, and often new transmission planning. At the same time, the United States is trying to reshore manufacturing. Semiconductor fabs, battery plants, electric vehicle factories, hydrogen projects, and advanced industrial facilities all need large amounts of dependable electricity. Then add electrification, more EV chargers, more heat pumps, more electric industrial processes, and more residential and commercial demand in growing regions. All of these trends push demand onto the same grid equipment supply chain. That is the real conflict. It is not just clean energy developers waiting for transformers. It is utilities, data center operators, industrial companies, municipalities, and renewable developers all trying to secure critical electrical hardware in the same constrained market. And when everyone needs the same equipment at the same time, the transformer becomes more than a component. It becomes leverage. This is where the issue turns geopolitical. For decades, energy security was often discussed in terms of oil, gas, pipelines, and fuel supply. The strategic question was, who controls the fuel? But in an electrified economy, another question becomes just as important. Who controls the hardware? Who makes the transformers? Who controls the specialized steel? Who has the factory capacity, skilled workforce, and ability to deliver large electrical equipment on time? The energy transition is not just about replacing fossil fuels with renewables. It is also about rebuilding the industrial base around electricity. Countries that can manufacture grid equipment at scale will have an advantage. Countries that cannot may find their energy ambitions limited by import dependence, long lead times, and global competition for the same machinery. For the United States, this is a strategic problem. America wants to lead in AI, rebuild manufacturing, expand clean energy, strengthen grid resilience, and reduce dependence on foreign supply chains. But all of those goals depend on electrical infrastructure. And electrical infrastructure depends on industrial capacity. A country can pass incentives, announce targets, approve projects, and attract capital. But policy does not automatically produce transformers. Factories have to be built, workers trained, materials sourced, designs certified, and production scaled. Utilities also need enough standardization and planning discipline to make the supply chain more efficient. That takes time. The geopolitical lesson is simple. The country that controls energy hardware controls part of the speed at which other countries can electrify. This does not mean every transformer has to be made domestically. Global trade will remain important. Imports can help relieve pressure. International suppliers can provide capacity the U.S. market needs. But deep dependence becomes risky when the equipment is strategic, expensive, slow to replace, and essential for national infrastructure. That is why transformers are no longer just utility procurement items. They are part of industrial strategy. They sit at the intersection of grid modernization, national security, manufacturing policy, supply chain resilience, and the race to power the next generation of the economy. But there is also a necessary nuance. The transformer shortage is real, but it is not the only bottleneck in the American energy build-out. Projects are also delayed by permitting, interconnection queues, transmission congestion, local opposition, labor shortages, financing conditions, and utility planning processes. In some cases, the transformer is the main problem. In other cases, it is one bottleneck among several. It is also important to distinguish between different types of transformers. A distribution transformer serving a neighborhood is not the same as a large power transformer at a major transmission substation. A generator step-up transformer for a power plant or renewable project is not the same as a smaller unit mounted on a pole. These markets overlap, but they are not identical. Lead times, materials, suppliers, design requirements, and procurement strategies can vary. So the point is not that every energy delay in America is caused by transformers. That would be too simplistic. The more accurate point is that transformers reveal a deeper weakness in the energy transition. The physical supply chain behind the grid is not expanding smoothly enough to match the speed of new demand. That is the bigger story. The energy transition is often described in terms of technology curves. Solar gets cheaper, batteries improve, EVs scale, data centers grow, demand forecasts rise. But the grid is not a chart on a slide. It is a physical system made of steel, copper, aluminum, concrete, rights-of-way, substations, breakers, transformers, and trained crews. And physical systems have inertia. They cannot be transformed overnight. This is why the next phase of energy strategy will be much more industrial than many people expect. It will not be enough to ask how much generation America can build. The better question is, how much of that generation can actually be connected? It will not be enough to ask how many data centers companies want to construct. The better question is, where will the power come from, and can the grid equipment arrive in time? It will not be enough to announce new factories. The better question is, does the local grid have the capacity, the transformers, and the substation infrastructure to support them? This is where serious energy planning begins. The transformer shortage shows that America's energy future depends on coordination between utilities, manufacturers, developers, regulators, and policymakers. Utilities may need better long-term procurement strategies. Manufacturers may need confidence to invest in new capacity. Developers may need to plan grid equipment earlier. Policymakers may need to treat grid hardware as strategic infrastructure. There are solutions: more domestic manufacturing capacity, more standardization, better forecasting, strategic reserves, refurbishment, smarter asset management, and better grid planning. But none of these solutions are instant. That is the uncomfortable truth. The shortage can improve, but the underlying challenge will remain. America is trying to electrify and industrialize at the same time, and both goals require a stronger grid supply chain. This is why transformers deserve more attention. They are not glamorous. They are not the face of the energy transition. They do not appear in most political speeches. They do not attract public excitement like solar panels, batteries, nuclear reactors, or AI chips. But without them, many of those technologies cannot scale at the speed people expect. A transformer is not just a box in a substation. It is a gatekeeper. It decides whether power can move from one part of the system to another. It decides whether a project can connect. It decides whether a load can be served. It decides whether infrastructure exists only on paper or becomes operational reality. That is why this shortage slowed projects no one could afford to delay. Because America is not simply building more energy projects. It is trying to rebuild the foundation of its economic power. The next industrial era will run on electricity. AI, factories, transportation, homes, buildings, military bases, ports, logistics systems, and critical infrastructure will all depend on a stronger, more resilient grid, and that grid will need transformers at every level. So the lesson is clear. The energy transition is not only a race for clean generation, it is a race for connection. It is a race to build the equipment that turns capacity into delivered power, and to align policy ambition with industrial reality. And in that race, the countries that win will not only be the ones that generate the most electricity, They will be the ones that can move it, transform it, and connect it on time. America does not just need more energy projects, it needs the industrial backbone that allows those projects to become real. Because in the next phase of the energy transition, power is not just about producing electrons. Power is about controlling the system that delivers them.